Investigate the graph of y equals some function plus some constant v by hand using a table with technology and then generalize. You will need graph paper or a page of grids that can be found at this website right here. This is part of the Family of Functions series. We will start our investigation with the squaring function y equals x squared. We're going to graph it using the parabola dance. We'd like you to do that right now. Press pause until you're finished. So 0 squared is equal to 0. That's the vertex. From there, right 1 up 1, because 1 squared is 1. Right 2 up 4. Right 3 up 9. And then on the other side, left 1 up 1. Left 2 up 4. And left 3 up 9. We could have also used symmetry to get those last 3 points, symmetry about the y-axis. Connect the points, and there's our parabola. Now, keeping an eye on this parent function, we want to graph y equals x squared minus 3. So we'll start by making a table that has 5 rows. I'd like you to go ahead and complete this table. Press pause until you're finished. So putting in the values for the table, and you can see how I got them here. Press pause if you need to see how those values were arrived at. Go ahead and plot those points. Press pause when you're finished. So those are those 5 points right there. And then we'll go ahead and connect the points. And we get y equals x squared minus 3 in green. So how are the graphs similar to one another? Well, they are the same shape, but how are they different? Press pause until you've thought about that for a few seconds. Well, you'll notice that from blue to green, it's down 3. Blue to green from that point, down 3. And from that point, down 3. And from that point, down 3. I'd also like you to compare and contrast using tables. So I'm going to move this table over to the right, and we're going to look at the y equals x squared table here in blue. So those are the values for the normal parabola. This is the one for the one we just graphed. So I'd like you to compare and contrast using tables. Press pause when you're finished, until you're finished. Well, it turns out that the x-coordinates are identical, but look at the corresponding y-coordinates there. Press pause until you're finished looking at them. So from 4 to 1 is minus 3, and hey, look at that. And from 1 down to negative 2 is minus 3, 0 to negative 3, 1 to negative 2, and 4 to 1. All minus 3, corresponding y-coordinates with the same x-coordinates. So all the coordinates, all the y-coordinates are down 3. You can see that in the equation, minus 3. So the phrasing we use is, we say that the graph of y equals x squared minus 3 in green has a vertical shift down 3 from its parent function y equals x squared, which is in blue. You can see it in the graph that it's down 3. You can see it in the table. All the y-coordinates are down 3. And you can see it in the equation, the minus 3, down 3. So we're going to repeat the same exercise, but with a different equation this time. This time we're going to look at y equals x squared plus 2, keeping an eye on the parent function in blue here. And as we did before, we'll make a table with 5 rows and using these values for x. So go ahead and complete the table. Press pause until you're finished. Make sure you've got these values right here. And then go ahead and plot the points. Press pause until you're finished. And so those are the 5 points plotted right here. Connect the points. Press pause until you're finished. And again, we get this parabola-looking curve here in green. How are the graphs similar? Well, as we said before, they are the same shape. And how are they different? Well, this one's a little bit different in a different way. So go ahead and press pause until you've thought about that. Well, you can see from this point from blue to green, it's up 2. From blue to green up to here and up 2 from here. We'd also like to compare and contrast using tables as we did before. So I'm going to move this table over to the right and look at y equals x squared right here. And this is what the normal y equals x squared table looks like. Press pause when you're finished comparing and contrasting these two tables. Well, you'll notice that the x coordinates again are identical in the tables. But look at the corresponding y coordinates. If you need to pause, go ahead and do so. But you'll notice from 4 to 6 is plus 2, from 1 to 3 is plus 2, from blue to green is plus 2 right across the whole, each one of in each table, each part of the table. And notice where that plus 2 also is in the equation. All the y coordinates are up 2. And again, the phrase we're going to be using is we say that the graph of y equals x squared plus 2 has a vertical shift up 2 from its parent function y equals x squared. We can see it in the graph. We can see it in the table. We can see it in the equation. So let's go ahead and generalize what we've just learned here. So the graph of y equals x squared, the parent function, and the graph of y equals x squared plus v, some constant v in green, are the same curve, it's the same set of points, but if v is positive, the graphs seem to shift up vertically, v units from y equals x squared. While if v is negative, the graph seems to shift down vertically, the absolute value of whatever v is, that many units from y equals x squared. Now the question is, does this vertical shift hold true for other functions besides y equals x squared? And so we're going to investigate that using TI-Nspire technology. Here the parent function is y equals x cubed in dashed blue, y equals x cubed plus some constant v outside the function here, and here's our slider that controls the value for v. Notice right now that the y coordinates are identical for both the blue and the green function. So let's change v to be positive 1. So the graph is y equals x cubed plus 1 in green here. Notice the graph, what's happened, and here notice what's happening in the table. Y equals x cubed plus 2. Y equals x cubed plus 3. And let's go ahead and make v negative, see what happens there. Y equals x cubed minus 1. Notice again the values in the table, what the graph looks like. Y equals x cubed minus 2, and so on. Here the parent function is y equals the square root of x in dashed blue, and the y equals the square root of x plus some constant, and the slider controls the value for v. Notice right now again the coordinates are identical. So I'll go look at y equals the square root of x plus 1. Notice what's happened to the curve, what's happened in the y coordinates. Y equals the square root of x plus 2. Look at the graph, look at the table. Y equals the square root of x plus 3, plus 4. And then looking at values for v being negative, y equals the square root of x minus 1. Notice where the green graph is compared to the parent function. Look at the corresponding table y values in the table. Square root of x minus 2, and so on. Here we're going to let y equals f1 of x be this blue dashed generic function, a piecewise function if you will, and then y equals f1 of x plus a constant being controlled by this slider here. Notice again sometimes the values are undefined because of it's only a limited domain. So let's increase v to be 1, and the green graph is y equals this function plus 1 unit, and notice what's happening to the corresponding y coordinates, and look at the graph. Y equals f1 of x plus 2, again notice the plus 2 is outside the function. Graph, table, f1 of x plus 3, y equals f1 of x plus 4. And then we can also look at it, y equals f1 of x minus 1. Notice how it compares to the parent function, both in the graph and the table. Y equals f1 of x minus 2, and so on. Next are three different parent functions graphed alongside those parent functions with a value v added either to the function or subtracted from the function. Notice the patterns between the graph and the value for v, the constant added outside the function. And of course, pause anytime as needed. So here our parent function is y equals the absolute value of x in dashed blue. Here's the absolute value of x plus 1 in green. Notice again the graph in the table. Y equals absolute value of x plus 2, the graph, the table. And notice the rest of these. Press pause anytime as needed. Here the parent function is y equals 2 to the x in dashed blue. Y equals 2 to the x plus 1 in green. Notice the graph and the table. Y equals 2 to the x plus 3, the graph and the table, and even the asymptote. Y equals 2 to the x plus 5. Y equals 2 to the x minus 1. And y equals 2 to the x minus 4. Press pause anytime as needed. And finally, here's another generic function. We'll just call this y equals f of x in dash blue, a piecewise function here. Here's that same function, plus 2, plus 4. Notice the table, notice the graphs. Y equals f of x minus 1, f of x minus 3, and f of x minus 5. Press pause anytime as needed. So let's summarize this when graphing y equals f of x plus v, where v is some constant outside the function. When v is greater than 0, that is, it's positive, the graph shifts up vertically v units, like a smile. When v is negative or less than 0, the graph shifts down vertically, the absolute value of that negative number, that many units. Down, frown. Now you try one just to see if you picked up on this. Graph y equals the square root of x plus 3 for the practice. Press pause to do this and then resume when you're finished to check your answer. And here's your answer. It's the square root function shifted up 1, 2, 3 units every single point.